Hello everyone. This is the final presentation for the LambdaBuffers project for the Catalyst Fund 9 milestone. The LambdaBuffers started a year and a half ago with the Catalyst Fund 9, and I'm happy to say that it was the support for LambdaBuffers was extended through Catalyst Fund 10, where we are planning on adding additional support for languages, concretely Rust, JavaScript, and Icon. I will just run through what the LambdaBuffers toolkit is and which problem it tackles and how it solves it. And finally, I will take you through the LambdaBuffers Cardano demo, which is one of the outputs necessary to close off the final milestone, and where we will show how concisely we can lay out a typical Cardano DApp project and how uh, much less code we have to manually write because of LambdaBuffers. So LambdaBuffers is a toolkit for sharing types and their semantics between languages. Let's unpack this a little bit more. So in traditional software engineering, programs are written in different languages, but at the end of the day, they have to communicate between themselves, communicate with certain messages encoded in certain format, like JSON, CBOR, XML, whatever. Writing how things are encoded and decoded is very tedious to maintain, to test for correctness, and it's just unnecessary and error prone. This has been automated away very effectively by the existing tools in this space, such as protocol buffers. Lambda buffers is essentially achieving the same thing uh, by introducing a couple of novel ideas and mechanisms. Uh, One thing that Lambda buffers tries to do is share type definitions between different languages, but also share semantics. What is semantics? So, given a certain type, a notion of equality can be defined for it. When in Lambda buffers, we specify a certain type and we say that this type supports equality, the same equality notion will be implemented in all of the supported Lambda buffers target environments, whether that is Haskell, PureScript, Rust, or whatever what comes next. We also support this notion of semantics through something called type classes that languages like Haskell already has, and PureScript as well. They are literally called type classes in those languages. And in Rust, this idea is called traits. So what we do, we can stole this idea have to have a way to manage not only how to specify types, but to say what types, which types get which semantics. So type A supports equality and JSON, whereas type B supports equality and Plutus data encodings. And this is a very useful feature to have in an environment like Cardano, where we are working in a very restricted environment where things like Plutus data encodings can only support a certain set of fundamental types. For instance, we are not working with floating point numbers in Cardano, but that's, for instance, not a problem in any other generic environment that you work with, like the web environment and stuff like that. So Lambda buffers is essentially a toolkit in which you specify your domain types and you specify which semantics those types have, and the whole pipeline essentially generates code that you can use seamlessly. And what LambdaBuffers also provided is Nix-based DevOps tooling, where this process of eh, including dependencies or code generation tooling being invoked in proper order and in proper manner is done for you. So you don't have to do much, but just to specify a Nix build recipe and reload an environment when you change your schema. So this is the main repo, and it contains of all the foundational elements of this project, namely the front-end compiler and Cogen. Front-end is basically an implementation of domain-specific language for specifying your Lambda buffer schema. There you specify in a textual format your types and tag them with the semantics that you desire. Compiler takes in form of that schema and checks whether everything lines up and is valid through a process called type checking. Once we have a properly type checked schema and there's no errors to be reported back to the user, um, the final step of the pipeline is invoked, which is called the Cogen. And there, the user just needs to specify which Cogen module in particular they want to use from the Cogen modules that we currently support, namely Haskell, PureScript, Plutus TX, and Plutarch. Yeah, so additionally, we had to build runtimes. So every time that you want to work with your Lambda buffers types and their semantics, you need to also include the Lambda buffers provided runtime libraries for your language ecosystem, which contains certain functions and implementation necessary for the Lambda buffers toolkit to operate properly. And one of the most difficult parts and the most crucial parts of this whole project was to have a comprehensive test suite that will make sure that the semantics between different languages are compatible. So if I perform an equality check in Haskell, the same on a value of a Lambda buffers type, the same check needs to result in the same result in PureScript, in Rust, in any of the supported, of the supported languages. For anybody interested in the repo, we have a very comprehensive documentation maintained in our GitHub pages that you can visit and read through the chapters where we talk about topics of design and internal APIs if somebody wants to contribute or find novel ways of using Lambda buffers. But we also have guides for particular language backends that can help users onboard Lambda buffers into their projects and get them started quickly. Let's move on to the Lambda buffers Cardano demo. This is the project that we built to demonstrate how to use Lambda buffers, but also to demonstrate how Lambda buffers makes Cardano DApp development a lot less involved and a lot more streamlined. The essence of this demo is the fact that we have the API of our protocol defined in our Lambda buffer schema. So here we can see that the schema defined in this file contains certain types. So there's a name called name of the module, certain imports that are very important that you can find out what they mean and why you need them in the documentation, but it's necessary to import Prelude and Plutus modules to work specifically with Cardano dApps. Here we can showcase how one can specify record types, and in that sense also specify polymorphic record types that consist of certain Plutus concepts such as asset class and address. Then we can see how the semantics management works using the derive statement, a lot like you would use derive in Haskell, PureScript, or Rust, basically. We also support a notion of a product type, which is a lot like a record, but the order of fields is essential. And we also have some types, which are sometimes called tagged union types, and sometimes called enum types. I think in Rust they're called enumerated types. So these are certain types that we specified for this demo protocol, just so we can showcase what Lambda buffers can do and how it is used. And for semantics management, you can see how here I'm kind of declaring that this sum A type supports the notion of equality, and also supports the notion of being Plutus data. Plutus data is one of the essential, the only encoding method we have in Cardano DApp development. And we spend a non-trivial amount of time um, um, managing these encodings between the language environments that we typically work with. Notably, we, for instance, specified our types, our datum types in Haskell, and then later on in transaction building environments such as Cardano transaction library, which is in PureScript, we have to kind of duplicate type definitions and implement all the Plutus data encodings manually, or with whatever tooling support that we have available like PureScript Bridge, which is not really production ready and reliable, or some kind of other method of dealing with this. So here, finally, we define two protocol entities, which I called EQ datum and EQ redeemer. And of course, we attach the EQ and Plutus data instances for them. And EQ datum is also just here to showcase what it can do. It contains like three fields, rect, prod, and sum, that instantiates the above specified types with a bytes type, and a redeemer actually denotes type of action that this protocol supports. So we will have two types of actions in this protocol. One is, hey, is this datum in this UTXO equal to this one in the redeemer, or is it not equal? And the script will either succeed or fail for that. Once we have our validators written, and we'll see later how we write them in both Plutarch and PlutusDX, these scripts have to be serialized and supplied through a transaction building component. Specifically, we here work with Cardano transaction library, which is a PureScript based environment. And so we have to write this configuration from Haskell and read that configuration from PureScript. And that is seamless. There's no code that you need to write in order to have that happen, other than just saying, writing a statement, read JSON that is of type config. So the validation folder essentially contains our validator, a single validator called the quality validator, written in two different backends that we support. One of them is Plutarch, and one of them, the other is PlutusDX. You'll see how all of the code is essentially this half a pager. Admittedly, the logic itself is not overly complicated. We just try to parse a datum of type EQ datum, and we try to parse the redeemer as well, and we try to check for equality, and that's basically it. But the most notable part is that we didn't have to write any type definitions and didn't have to write any wiring and didn't have to write any instance implementations. This is all handled by the LambdaBuffers toolkit. And the imports here kind of reveal that fact. Here we import LambdaBuffers demo Plutus.plutarch to denote the difference between Plutarch and the native Haskell types. We import the EQ datum and EQ redeemer types with all of its constructors. Again, you can refer to the LambdaBuffers documentation to understand exactly how type mapping works, but it's fairly straightforward. And we do another additional imports of our runtime libraries to make sure that everything works as intended and all the instance implementations are loaded. If we go into the demo Plutus TX, we'll see the same validator written with Plutus TX, and again, we just have two imports from LambdaBuffers, and all of our type definitions and all of our implementations and semantics is loaded from these modules. So the validator can proceed, and the engineer can proceed and just work with the essence of the validator, which is its logic. Doesn't have to deal with any of the wiring. Here, the same logic is performed. Another innovation that LambdaBuffers put forward, because every time you work with like automated code generation tooling, it's kind of pointless if there's no DevOps tooling that can help you wire everything together. So on one side of this pipeline, you have the specification of your types, like the Lambda buffer schema. And on the other side, you actually have code generated and packaged source code, automatically generated source code that has to be packaged in a certain format. For instance, in Haskell, it has to be packaged as a Cabal package. In PureScript, it has to be packaged as a Spago package, and with Rust cargo and all that kind of stuff. So we innovated in this area and use Nix, the modern Nix practices, to make sure this is seamless for users. So every time you see a build.nix file, this actually contains what's called a flake parts module, where all the build rules and build recipes, depending on your nomenclature, I would say that recipes is a good enough term for this, are defined. And here we just basically say and provide to the users from the LambdaBuffers repo a way to say, this is my schema. Please generate Haskell Plutus support. This is my schema. Please generate Plutus PureScript support, which is going to generate and provide all the necessary runtime dependencies for working with CTL. And we say the same with Plutarch and also for vanilla Haskell and PureScript when we deal with the configuration that's agnostic to the Cardano environment. So every subproject, this is essentially a monorepo, every subproject has such a build.nix file. And the README of this project contains exactly the instructions on and the guide on how to effectively work with this. Here we specify our Haskell project and all the dependencies. Here you can see that we have to provide with the base schemas, which are LBF Prelude and Plutus. And we also have to provide the runtime libraries. So every time you see LBR prefix, that's a runtime library coming from LambdaBuffers directly. And here we also can include the demo API. So both the Plutus and config schemas are generating into Haskell code, and this is the place that we provide this generated code uh, to the build and development environments. It's quite seamless. So the only overhead for engineers is to specify this build.nix file, and that's basically it. And then if we go into the transactions folder, this is where we build and test our transaction. We're gonna add, as we proceed with our support with Catalyst Fund 10, we're gonna add Rust transaction building component here and TypeScript transaction building component here, just to demonstrate how a single monorepo with Lambda buffers can be concisely defined. But for now, we only support Cardano transaction library, and this is a standard boilerplate configuration that every CTL project has to have, which is admittedly a bit formidable, but that's unrelated to Lambda buffers. Here again, we have a build.nix file where we concisely specify how to build this project with Nix, and here again we just specify all the necessary dependencies, most notably the automatically generated uh, automatically generated code that came from Lambda buffer schema. At the end of the day, in this CTL project, we just have the um, transaction building logic again, which doesn't duplicate any work when it comes to type definitions and implementing encodings and equality for Lambda buffers types. It just does an import and everything else just works. So here we provide uh, three fundamental uh, transactions in this protocol, which is to create a value, the EQ datum, and store it at the EQ validator. And the other one is to create a transaction to check whether a stored value is equal to a provided redeemer or not equal to the provided redeemer. It's just a silly protocol, but useful to test the entire feature set of Lambda buffers. And in the test, we essentially go through a flow where we read the configuration both from the Plutus TX and Plutarch um, uh, projects. Both of these projects output a configuration that has a JSON format, a Lambda buffers JSON format to that point, but that doesn't matter because the software engineer and developer will never really care about how the file actually looks like, because it's Lambda buffers takes care of that responsibility and makes sure that what is written from one supported language environments can be read by another. So here we have two different components, like the Plutarch written validator and the Plutus TX written validator. Both have a CLI tool that can output a configuration that contains the CBOR encoded script, and this is loaded in this Cardano transaction library environment in this test suite. And the only thing, well, the set of imports here are formidable, but that's just pure script. As is customary now, the only overhead that the software engineer has is to simply provide the necessary imports. So here we import our config and the Plutus types, and we proceed to work with that. So the essential flow of this test suite is to read both configurations, get both versions of the same script, and go through the same flow with the both scripts. The flow goes like the following. So we first store an example EQ datum at the EQ validator, and then following that, we try to compare that to equality with another example datum, and then compare that to be unequal with another, and make sure that the logic checks out. When we repeat the same flow with both versions of the script. And this is how this generally looks like. And this is uh, the end flow. So the whole project uh, essentially looks the same, but what we managed to delegate to the LambdaBuffers tooling is the annoying part of making sure that types are specified in one place, and code generation kind of helps us to have this types and their semantics available in all the languages that we work with, so we don't have to duplicate any work, any tedious and unnecessary work. We provided the README that will take you in more details throughout this project, and will tell you how to kind of dig more deeply and inspect bits and pieces of the project itself, but also Lambda buffers and how it works, and what are the good ways of debug any potential issues. At the end of the day, uh, this this project and repo is equipped with a CI that performs the checks we just talked about. And here's an output of a successful check run. And if you go to the repo itself, you will see that this nice green little check mark tells you that the test suite passed. And you can visit the test suite by simply clicking on this green button, and the PureScript demo.ctl check that's run in Node.js actually runs plurip, which spawns a private network cluster and actually tests the whole flow against a real network, a private network that we just spawn and destroy after the test suite is done. And here we can see that both tests are passing. That's it. Thank you very much for your attention. Hope this was good enough.